Okay, folks, I apologize if the audio is a little bit low quality, but we're going to run with it. We are now to the coolest part of nuclear chemistry. That is transmutation. Mutation means a change of some sort. Transmutation is the process of one element changing into another element by emitting particles or by emitting radiation. We know that an element is basically defined by a certain number of protons and to some degree the neutrons. Well, if we can change the number of protons and neutrons, then we'll have a new element. And that can happen when an atom gets rid of some protons and or neutrons. Okay? Now, when we talk about this, it's important to talk about the decay mode. The decay mode just means the type of radioactive particles that are emitted. What are we talking about? Things that we've been talking about already. Alpha particles, which are just like a helium nuclei. Okay? Or beta particles, which that's a fancy word for electrons. Or positrons, which are those anti-electrons. They're like the opposite of an electron. They have a positive charge, but no mass. Okay, so those are the particles that can be emitted, and in that process, one element can change to another element. So there are two types of transmutation. There's natural and there's artificial. Okay? Natural transmutation is spontaneous. It just happens. If you have a naturally radioactive element, it will undergo spontaneous natural transmutation. There's a list on table N of radioactive elements and what decay mode they will go through, meaning what particles will be emitted as they go through natural spontaneous transmutation. You can identify natural transmutation because there's only one reactant. You have one element, it is unstable, it is radioactive, it will go through natural transmutation. Artificial transmutation, you can probably guess, is done by humans. This is when we force transmutation to happen. How? We bombard an atom with some particles. Okay? So in this case, there will always be two or more reactants. So there will be the atom or the element that you start with, and then the particle or particles that you bombard it with. So there will be two or more reactants in artificial transmutation. One example of this would be nuclear fission, which is what happens in nuclear reactors, which we use to generate electricity. Okay, we'll talk more about that in another lesson. Okay, so we got natural transmutation, which has one reactant. Artificial transmutation has two or more reactants. Okay, so let's try writing a nuclear equation. All right, here we go. Now there are three simple steps to this, and they will look pretty mysterious until we do an example. So let's just get these steps written down. First, you look on table N, and you know what atom or what element you're starting with, and so you have to find its decay mode. What particles does it emit when it goes through transmutation? What is emitted? Then you write a skeleton equation. Table O will help you with this to write in the correct notation for the particles that are emitted. Okay? Then you're going to fill in the missing particle. That will be the new element that is created, actually. And to figure this out, we will follow the rules of conservation of mass and conservation of charge. Okay? So get these written down, and then hit pause, and then I'm going to show you an example, and this should make a lot more sense. Okay, we're going to start with francium, francium-220. If you look in table N, okay, table N, francium 220, it's about 7 down on table N. And you can see that if you look in the decay mode column, it goes through alpha decay. All right, so what do? We say that means francium is going to break into a couple of things. One of the things it breaks into is an alpha particle. That is one of the things that will be emitted. An alpha particle is a helium nuclei with a mass of 4 and a charge of 2. Okay, so francium breaks into this, but there's something else. We're going to draw a plus sign and then a box, because basically we're saying francium breaks into a helium nuclei and something else. How do we figure out the other thing? We follow the laws of conservation of mass and conservation of charge. What that means is the mass on this side has to add up to the total mass over here. So 4 plus something has to equal 220. I think you can see that, okay, well, whatever this is, that should be 216, because 216 plus 4 equals 220. So whatever this particle, this thing is, it has a mass of 216. The charge, over here the charge is 87 protons. Helium has 2, That means whatever this is, it's got to have a charge of 85 protons. Now we've got a really strong clue right here of what element this is. There's only one element that has a charge or that has 85 protons. That's astatine. This has to be astatine because only astatine has 85 protons. So when francium goes through alpha decay, it basically releases an alpha particle and turns into an atom of astatine. Okay. All right, let's try one more example. Next example is going to be calcium, calcium 20. Find calcium 20 on table N. Okay, it's, where is it? Let's see, calcium 20, where the heck is it? Sorry, calcium 37. Find calcium 37, and that's a lot easier. It's 3 down, okay? So calcium 37 goes through positron decay because there's a beta plus in the decay mode column. So what that means is calcium will break into a beta particle plus something else, okay? So since beta particles have no mass, whatever is left here will have a mass of 37 because 37 plus 0 has to equal 37. And then beta particle has a charge of +1. This has a charge of 20. So whatever the charge is here has to be 19. 19 plus 1 equals 20. We've obeyed conservation of mass. We've obeyed conservation of charge. Now, this is our big clue. What element is this? Well, what has a mass, what has a charge of 19? Or what has 19 protons? It has to be potassium. Potassium is element number 19 on your periodic table. It has 19 protons. So that's the only thing that this could be. So now we figured out that when calcium goes through transmutation spontaneously, it emits a positron, which is a beta plus particle, and it turns into potassium, potassium 37. Okay. Now let's try one more example that's kind of weird. Carbon 14. Carbon 14, if you find it on table N, carbon 14, second one from the top, okay? That goes through beta decay. So it gives off a beta particle, and then there will be something left over, some new element. Okay, now the mass is pretty easy. You can see that, okay, whatever this is, it's going to have a mass of 14. Now the charge, this gets a little weird. This is a -1. Over here, there's a 6. Whatever this charge is for this particle, this side has to add up to 6. That means this is a 7. Okay, 7 plus -1 equals 6. Just keep the math simple. Okay. Then what atom is this? Well, what has 7 protons? What has a charge of +7? It's element number 7. Okay. It can only be nitrogen. This is nitrogen. Now, the reason this may seem really, really weird to you, the reason this happens is technically a neutron decays to a proton and an electron. That's how we end up with seemingly an extra proton that we didn't have before. I can talk to you a little bit more about that in class. But as long as you make sure that the math on this side matches the math on this side, -1 plus 7 equals 6, everything's going to be okay. All right. And let's see. Okay, now you're going to do the transmutation worksheet and work on assignment 6 and possibly something else too. Check the checklist that Mr. Young has given you. Okay.